Hey scholars, welcome back. Remember how I was saying the first lesson was super front loaded, and as we progress through the weeks, the lessons will get progressively later? Well, today's is one of those lessons. Today we're going to calculate the end behavior of a rational function. So we started looking at it in the previous lesson, but we are going to really hammer out and establish some guidelines or some structure that we can use to allow us to be more efficient moving forward into our more advanced mathematical classes. So we can generalize from specific rational functions to state relationships between the end behavior and the degrees of the numerator and denominator. That's what it all boils down to, which is why we spent so much time in the beginning of this unit really hammering out and ensuring that we were 100% positive about what those words actually represented. All right, and ultimately our goal is to find the end behavior of a rational function after rewriting it as a quotient and its remainder. So in 2000, the EPA reported a combined fuel efficiency for cars that assume 55% city driving and 45% highway driving. They have used this expression here, 100xh divided by 55x plus 45h. Several conventional cars have a fuel economy for highway driving that is about 10 miles per gallon higher than for city driving. So they tell you that we can represent h as the quantity x plus 10. So I'd like for you to write a function using this original function that represents the combined fuel efficiency for cars like these in terms of x only. So we need to make some type of substitution. That way we can perform some type of division in our second question. And I did not include a table or a blank space here because I figured, you could work it out on a piece of paper and simply type in your response here. If you are really struggling with the division, we can work that out together in class. But by this point, I will go out and make an assumption that you have at least a proficient grasp of that concept. Now, why is that so important? What is this idea about fuel economy? So car advertisements often feature fuel efficiency by stating how many miles a car can travel per gallon of gasoline. It's obviously measured separately for highway and city driving because cars on the highway usually have a better fuel efficiency and smaller vehicles have a better fuel efficiency than larger vehicles. So going back to question 2, when you rewrote this rational function as a quotient plus its remainder, what can we say about the end behavior of f as it pertains to this particular situation? So as you start to increase that value of x, what is ultimately happening in this context? And should we consider abnormally large values of x for this particular context, or is there like a limit on the domain of the function um, regarding the fuel economy? So that's where I'm actually going to pause this video because tomorrow we are going to, like I said in the beginning of this video, we are going to spend some time talking about this idea of how does the degree of the numerator and the degree of the denominator lead to a more efficient description of the end behavior. So you just got a sneak peek of the next slide, but that's where I'm going to pause this video.